If you've taken an algebra class before, it is likely that you've heard the term PEMDAS, or perhaps the phrase, "Please excuse my dear Aunt Sally," or "Purple elephants may destroy a school," or maybe even "Pancake eating makes delicious afternoon snacks." Okay, you know what, you're right. Nobody actually says that last one. While these can be extremely silly mnemonics, we do learn them for a reason, as they can help us remember a really important element of math, namely the order of operations. You've probably heard this phrase before too, right? Order of operations. But what does that mean, and why do math teachers obsess over it anyway? Well, because it's about clarity and precision of communication. It might not feel like it all the time, but the goal of the order of operations is really to minimize confusion. Consider a simple example. If we wanted to add two numbers together, say 4 and 5, this would be no trouble. Addition is an operation which we've known for probably what feels like our entire lives, and so we can easily determine 4 plus 5 is equal to 9. And for the most part, as long as we only use one operation at a time, we've got nothing to worry about here. But what if we wanted to use two different operations together, perhaps also multiplying that 5 by 2? We would write 4 plus 5 times 2. Now, you likely know pretty quickly that this is then equal to 4 plus 10, which is then equal to 14. But that is only true because multiplication comes before addition, because we have an established order in which we perform those operations of multiplication first and addition afterwards. We know ahead of time to evaluate the expression in this way. On the contrary, you might suggest a reasonable way to read the expression 4 plus 5 times 2 would be to read left to right, first performing the addition operation 4 plus 5 equal to 9, then multiplying by 2, giving us 18. Now, if you're anything like me though, this likely feels dirty and sacrilegious, but without first establishing the order of operations, there's actually nothing inherently wrong with this. This does give us a different result, however, so establishing an agreed way to interpret this ahead of time is critical in order to make sure that we're all on the same page in terms of how we're communicating these ideas. We want everyone to read the expression 4 plus 5 times 2 and know without a doubt that it means 14. The order of operations help us remove the ambiguity. Now, the order of operations you're likely familiar with from algebra probably looks something like this. P for parentheses, E for exponents, M for multiplication, D for division, A for addition, and S for subtraction. But this isn't something that is exclusive to algebra. In fact, when combining different operations like intersections, complements, and unions, we'll need something similar for set theory as well. And in fact, it will almost be exactly the same. First, we will still begin with parentheses. These serve as a useful visual tool for separating expressions in writing, and so if we were to write something like the complement of A union B, this would tell us that we need to union A and B first, then take the complement of that result. Just like we would if we were given the expression the quantity 3 plus 4 squared, where we would first add 3 and 4 to get 7, then square to get 49. Next is the same as well as we would evaluate complements. How are the complements the same as exponents, you may be wondering? Well, the order of operations is actually less about exponents specifically and more about superscripts in general. Exponents are written as superscripts, and complements, whether as an apostrophe or a little c, are as well, and so they go second. For example, if we were going to take A complement union B, we would first find A complement, then combine that with the set B. Just like if we had to evaluate 3 squared plus 4, we would first square the 3 to get 9, then add the 4 to get 13. In place of multiplication and division, and I should note here that multiplication and division are in the same tier, if you will. In other words, they're going to be read left to right. This is because in some sense they're actually the same operation, but I'll discuss that more in another video. But in place of multiplication and division, we can fill in with things like the Cartesian product. Now, this isn't necessarily something we'll use much for our purposes, so we'll just leave this here for now. What we will focus a lot on, though, is unions and intersections, which fill the role of addition and subtraction respectively. These, just like multiplication, are in a way the same operation and thus belong to the same tier, so we're going to evaluate these left to right as well. And so we have the same basic order of operations. First, parentheses, second, superscripts, or in other words, complements, 3, products, and 4, sums, in other words, unions and intersections. Let's try this out on a few examples. Let's consider the set of digits. This will be our universal set for this problem, remembering from episode 6 that the universal set is the set of everything being considered in a particular problem. So here, u is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let's also let a equal to 1, 2, 3, 4, and let b equal to 1, 3, 5, 7. We can draw the following Venn diagram to include sets a and b, placing elements 1 and 3 in the center, as they are shared by both, 2 and 4 in the region exclusive to a, 5 and 7 in the region exclusive to b, and 0, 6, 8, and 9 outside, belonging to neither a nor b. First, let's find the complement of a union b. From our order of operations, we know we need to begin with parentheses, so we'll look inside and evaluate a union b. Since the union takes all of the elements that belong to either set, a union b is going to equal 1, 2, 3, 4 from set A and 5, 7 from b. Next, we can take the complement. The complement is all of the elements in our universe that do not belong to the set, so we exclude everything from our previous step and include everything else. This gives us 0, 6, 8, 9 as a final result. Next, let's look at the complement of the intersection of a and b. This will function similarly, except here we will be using the intersection instead of the union. Again, beginning with what's inside the parentheses, we'll start by evaluating a intersect b, which is 1, 3, as these are the two elements that are common between the two sets. Then taking the complement, we have everything else that belongs to the universe that is not 1 or 3, and so 0, 2, 4, 5, 6, 7, 8, 9 as our final result. If we want to find, say, a complement intersect b complement, we still apply the same order of operations. Here, there are no parentheses, and so we'll move to complements first. A complement is all of the elements that don't belong to set A, so 0, 5, 6, 7, 8, 9, and B complement is all of the elements that don't belong to set B, so 0, 2, 4, 6, 8, 9. Next, we would have products, though this doesn't apply here either, and so we'll move to evaluate unions and intersections. Taking the intersection of the set 0, 5, 6, 7, 8, 9 and 0, 2, 4, 6, 8, 9, we have the common elements of 0, 6, 8, 9, which is then our final result. Lastly, let's evaluate A complement union B complement. Here again, we have no parentheses, and thus we'll begin with complements. And just as in part C, this is going to give us 0, 5, 6, 7, 8, 9 and 0, 2, 4, 6, 8, 9. Except here, we will be taking the union instead of the intersection. Combining these two sets, taking all the elements that belong to either, we have a final result of 0, 2, 4, 5, 6, 7, 8, 9. Now, if you've been paying very close attention, you might have even noticed that the answers to part A and C, as well as the answers to part B and D, actually match. This isn't a coincidence and is something we'll explore in our next video. But for now, hopefully this video has helped you get a sense of how to apply the same beloved order of operations from algebra to the context of set theory, and perhaps why it is so important as well. If you do have any questions, don't hesitate to put them in the comments below. Otherwise, I hope you have a great rest of your day.